Hi everyone, my name is Nicolas Guénaud. I'm a PhD student at the Lydie Laboratory in CEA in Paris-Saclay. And today I would like to introduce you to entanglement and decoherence in the context of attosecond photoionization. Before talking about decoherence per se, let's recall what we mean by coherence. So it's a central concept both in classical and quantum physics. In optics, it is widely used to describe the properties of light sources and their ability to produce interferences. So for instance, a temporally or spatially coherent source like a laser will have a stable phase in time and space, and it will show clear interference patterns like displayed here with a double slit experiment. And similarly, in quantum physics, a system can be in a coherent superposition of states, like the qubit states that are represented here on the Bloch sphere. And in such a superposition, the relative amplitude and phases of the components are well defined, and it allows the states to produce interferences. But in both cases, the notion of coherence is closely linked to the possibility for the observer to witness interferences. And decoherence will be about losing the contrast in these interferences. So now about photoionization. So it's the process in which an atom or a molecule absorbs a photon and subsequently emits one of its electrons, resulting in the formation of a positively charged ion. So this phenomenon is inherently attosecond, and therefore it requires the use of ultra-short laser pulses to probe its dynamics. Such short pulses have a very broad spectrum in the energy domain, which leaves the photoelectron in a large and continuous superposition of kinetic energy states. So now, when only one ionization pathway exists, you can simply write your bipartite system as a single tensor product of the electronic and the ionic state. But depending on the atomic or molecular species that you're looking at, photoionization can take place through multiple channels. So for instance, due to spin-orbit coupling, different vibrational levels of your molecule, or different electronic configurations. And in this case, the wave function is no more separable, and you can associate basically each peak in the photoelectron spectrum with a specific ionic state. So you see here there are two contributions in pink and blue here, coming from two different ground states through pathway A and B. And what happened is that these two contributions do not factorize by either the electronic or the ionic wave function. And this means that there is some entanglement between the photoion and the photoelectron. At this point, however, the total system is still in a coherent superposition, and it has not lost any of its coherence. However, in practice, it is actually very hard to measure the total wave function of your system, and you usually have access to only one part of it, so either the electron or the ion. But now that we have entanglement, the question is, how can you write the state of the electron or the ion individually? What is the effect of a partial measurement on your system when you do not measure all of its degrees of freedom? Well, here the quick answer is that because of entanglement, it's impossible to write either of the subsystem with a wave function. So they cannot be written as a coherent superposition where amplitude and phase have a well-defined relationship. Because what has happened is that a part of these relationships have been lost in the incomplete measurement process. So what you should remember is that entanglement can result in a loss of coherence in your subsystem as a result of this partial measurement. So when no wave function description is appropriate anymore to describe your subsystems, then one has to adopt the density matrix formalism. So a density matrix is like a quantum version of a covariance matrix. It is a positive emission matrix whose diagonal terms give the populations, and its off-diagonal terms basically encode how strongly the quantum states are coherently coupled to each other. So here the density matrix of the total system is defined as the matrix product Kepsi Brapsi. It is possible then to derive from this density matrix what is called a reduced density matrix for each of the subsystems. So here, for instance, for the electron, it can be written like this. So it is reduced because we are tracing over the degrees of freedom of the other particles. And the trace operation, basically, it's a mathematical operation that translates our lack of knowledge of the rest of the subsystem, the one that we don't measure. So similarly, for the ion, we can derive it this way. And now here on the left, in this case, we have a photoelectron spectrum with a clear separation in the two contributions here. So this means we have a maximal entanglement between the photoelectron and the photoion. And only the population terms will appear in the reduced density matrix of the ion. The coherence terms here between the two ionic states, so of the diagonal, are zero. And here what it means is that the entanglement has erased all coherence in the ionic subsystem. Now, in the case where the two pathways are energetically closer together, then the ionic density matrix is not that simple anymore, because basically we cannot decipher the origin of every photoelectron. Here there is some indistinguishability in the pathway of the electrons, and the density matrix only writes itself like this, with coherence term ρ12 and ρ21 that are different than zero. It can actually be shown that they are proportional to the spectral overlap here of the two contributions. And from there, we can derive what is called the degree of coherence, G, between the two ionic states, G1 minus 1 and G2 minus 2. And we will see in the next slide how it is a relevant information in a quantum experiment. But here, if we go even further to the case where we cannot distinguish at all the two pathways, then the system becomes separable again. And there is no more entanglement, which means that we recover the full coherence in the ion with a degree of coherence of 1. So now going into the actual experiments, it was Koulil-Makis and his team that first demonstrated their ability to measure the density matrix of krypton ions here. Their experiment consisted in ionizing krypton atoms with a femtosecond infrared laser pulse, leading to a coherence proposition of the spin-orbit coupled ionic states, which are then promoted by an XUV attosecond pulse to a final state where interferences could be witnessed as a function of the time delay between the two pulses. What the experimenters computed is that when considering a 7.6 femtosecond pulse, then the degree of coherence is quite low in the ionic subsystem. But when decreasing this pulse duration to about 3.8 femtoseconds, then the degree of coherence jumped to 60%, basically because of the larger indiscernibility in the photoelectronic spectrum. So in these conditions, when there was a 60% degree of coherence, the absorbance of the XUV at the level of the final state, 3D 3 half minus 1, shows a clear interference pattern with a high contrast. And you can convince yourself that this oscillatory motion takes place between the two spin-orbit coupled states, as the period of the oscillation is equal to the inverse of the energy difference of the spin-orbit coupled state. Therefore, as explained by Olga Smirnova, the experiment clearly shows how a coherent dynamic can be observed as a result of a limited entanglement between the photoion and the photoelectron. And this is only possible because of the ultra-short laser pulses, which led to a large indiscernibility in the ionization pathway of the electrons. In this way, Koulil-Makis and his team observed for the first time balanced electron motion on the attosecond timescale. One step further is the experiment from Mark Varking and Lisa Maricol that showed a way to control the degree of electron-ion entanglement emerging from the photoionization of H2 molecules, and thereby modulate the coherence between its vibrational ionic states. In this experience, a sequence of 2 attosecond pulses is used to produce spectral beating that will ionize the H2 molecules. And when this beating frequency is tuned to the energy gap separating the vibrational eigenstates, V equals 0 and V equals 1, then the bipartite system is separable and the coherent dynamics are observed on the ion side. In this case, the simulated density matrix shows non-zero off-diagonal terms. Conversely, when tuning the beating frequency to half the energy spacing of the vibrational states, then the entanglement is maximal because one can distinguish the vibrational origin of the electrons, given their kinetic energy. In that scenario, ionic states show little to no interferences, signifying a reduced degree of internal coherence. And on the density matrix side, one can clearly see that we lost many coherence terms of the diagonal. So with their setup, Wracking and Cole therefore showed a way to control the degree of entanglement from having close to no dynamic in the ion to a point where coherence is retrieved and oscillation can take place in the ionic state. The two previous studies addressed decoherence in the ion's internal degrees of freedom. It would therefore be interesting to examine whether a similar effect appears in the electron's degrees of freedom. To that end, a method named mixed-frog, developed by Charles Bourassa-Boucher, first demonstrated its ability to reconstruct the photoelectron's reduced density matrix. To perform a mixed-frog, one can use, among others, a train of attosecond XUV pulses to ionize atoms or molecules. An attosecond pulse train corresponds in the energy domain to a series of discrete peaks known as harmonics. They will form the diagonal terms of the electronic density matrix. An intense femtosecond IR pulse is then needed to drive continuum-continuum transition of the electronic wave packet. The role of the IR pulse is to induce interferences between the photoelectrons coming from all different harmonics as a function of the time delay between the two pulses. The strength of these interferences indirectly gives access to the coherence terms in red of the diagonal. The measurements are then processed using an advanced mixed state retrieval algorithm, which enables the reconstruction of the reduced density matrix of the electron. The results shown here are derived from measurements in neon that were performed in the Liddy laboratory on the ATTO platform. And here you can see that clear signs of decoherence appear on the reconstructed density matrix, especially between non-adjacent harmonics. Here, the purity of the electronic wave packet, which is an indicator of the coherence, is very low, and which it leads us to consider other sources of decoherence that are not quantum this time. Here in this article, the authors attribute methodically this decoherence to two main sources. First, the fluctuations in the XUV infrared synchronization, and then, second, the limited resolution of the detector. On one hand, non-adjacent harmonics have no coherence, or almost, mainly because the contrast in the oscillation is lost due to ensemble averaging related to the laser XUV synchronization. So indeed, if you want to see a signal oscillating at, let's say, 400 attoseconds, but your time jitter here is about 800, then you won't see anything. On the other hand, decoherence coming from the spectrometer results as an elongation along the diagonal of the density matrix, because basically the same photoelectron can be detected at different energy values. So in such conditions, instrumental decoherence masks the effects of ion-electron entanglement, which could also contribute to coherence loss here in neon. But this experimental decoherence is closely related to the broad energy spectrum of the electronic wave packet to characterize, given that the oscillation period of the interferences to measure is inversely proportional to the energy difference. And indeed, as Laurel and his co-authors demonstrated in a similar setup, by focusing on only a single harmonic, they were able to mitigate the instrumental decoherence coming from the resolution of the spectrometer and have a purity of almost 1 for a system where there was no entanglement, like helium. They could then quantify and attribute coherence loss in the electronic wave packet to ion-electron entanglement in argon, where entanglement was expected to take place. However, by focusing on only one harmonic here, the Kraken limits itself to the study of femtosecond dynamics, while the mixed frog density matrix that is showed here gives access to attosecond dynamics. Now, here I'm only showing you asymptotic density matrices, but a new method recently showed a way to reconstruct the evolution of the density matrices as a function of time. And this is what I would like to show you to end this tutorial. So here Berkan and his co-authors simulated the evolution of the electronic density matrix as the ionization process is taking place. So here they chose a setup that is really similar to the one of McVracking that I introduced to you in the middle of the video. So you basically have two XUV pulses that are separated in time and that will ionize your H2 molecules. Now, the temporal spacing of the pulses is set to produce a spectral beating that will maximize the entanglement, as we've seen before. And what one can see here is that before the second pulse arrives, so in this region, the purity of the electronic wave packet is close to 1, which indicates that there is a high degree of coherence in the electronic wave packet, or that there is no entanglement between the ion and the electron. But as the second pulse arrives here, the purity decreases strongly, and the coherence terms in the density matrix seem to vanish. Therefore, this simulation shows how the entanglement and the decoherence builds up on the attosecond timescale. And what is important to note here is that this simulation was realized using only the asymptotic density matrix as an input. So the density matrix after all interactions are over, like the one we could get from a Kraken or a mixed frog measurement. And this method is therefore very powerful as it can be used directly from the experimental results. So that's it for this tutorial. I hope it was interesting to you, and I guess I'll see you around.